As countries continue to grow and technology evolves, the demand for energy increases as well. To solve this problem without destroying our planet with carbon dioxide emissions, a focus must be placed on developing renewable energy sources. One way to make solar energy arrays more viable is to create a battery storage system that can provide power when the solar array is unable to generate enough power. This is what Team 10 has been requested to solve. The task is to create a hydro storage system that will use extra energy from a solar cell system to pump water that will be released at a later date to generate energy acting as a battery. The goal when working on this project was not to build a hydroelectric system, but to instead model the storage system with its energy consumption and generation. Using this, an efficient and cost-effective system is created that is able to be replicated in an actual location at a later date. However, not any solution is acceptable for the build of the storage system. And because of this, Team 10 also had to create an optimization function to help run through all of the possibilities of components and give us a selection of the best results. That way, only the best hydro storage system will be finalized and built. For the storage system, tight specifications were needed so that all customer needs are met. An initial, very important requirement is the amount of power that the hydro storage system must generate in 12 hours. The energy required to meet the needs of the system is for it to generate 120 megawatt hours from the reservoir releasing into the turbine. This amount of energy must be generated so that those getting power from the solar array are still able to get an equivalent amount of power when the solar array is inactive and reliant on the hydroelectric system. Another factor of the development is that the hydro storage system must be efficient. The purpose of this need is that energy is not wasted by inefficient components being present in the system. The higher the efficiency of the system, the closer the power output is to the power input from the excess solar energy when the system is active. The efficiency specified for the system was for it to be at least 75% efficient between the energy output and the energy input. If the power generated is 75% of the power input by the pump pushing water into the reservoir, it is deemed efficient enough to be conclusive in meeting the efficiency need. The most important factor is, in fact, the cost. The cost is the total price of actually implementing the optimized design in the specified location. The price must be compared to the efficiency of the system to get the best price for the realized efficiency. Because of this, Team 10 analyzed that the specification for the price of the project should be less than $550,000. The specifications helped us bring together a model that would best suit the customer's needs and fall between their desired building and energy production constraints.
To develop the model, our team had to solve for key factors and equations that allow us to determine if a certain model would be optimized for efficiency while keeping a low cost. Using the universal accounting equations, we had solved for the total mass of the water within the reservoir, the velocity of the water traveling up to the reservoir and down to the river, the energy required to go into the system, and the time it takes to fill and drain the reservoir of the water. Our team was able to validate these equations using the sample inputs and constants given, and the outputs given by our equations had successfully matched the sample outputs, proving that our equations had worked. Our team then needed to consider other factors of energy loss. Our team looked at thermal expansion of pipes due to the climate being too hot or cold on any given day. Our team researched the effects of what thermal expansion could do to pipes and if it could have possibly damaged the pipes, causing possible leaks, which could lead to future costs. From our research, thermal expansion of pipes should not cause any damage to the pipes if the pipes are given enough room to expand. When it comes to a colder day where the pipes could compress, this would be dependent on what type of pipes are being used. Going off the assumption that the types of pipes that are being given by PipeShack, the piping company that provides only the finest pipes, can withstand this compression, our team does not believe that the thermal expansion of pipes would have any effect. We validated our belief by using an equation that solves for the change in diameter of pipes when there is a change in temperature. Using different types of pipes, such as copper, steel, and aluminum, and having a change in temperature of around 20 degrees Celsius, the pipe's diameter would only change on average around 0.005 meters, which would have a negligible effect on our energy equations. Knowing this, our team decided to not include this factor into our energy equations. With our energy equation finalized, our team moved on to which zone should be chosen for our reservoir. In order to make an unbiased decision, we used the quality function development chart as a means to compare each zone. We agreed upon 4 customer needs that could represent each necessary component of each zone. A low base cost of installation, excluding the cost of building the actual reservoir, since this was one of the components that needed to be optimized and is not a constant value. A low additional future cost that we could face for building a reservoir on a certain zone. a low complexity shape of the land, meaning how does the land bend in between the reservoir and the river, and a small distance between the reservoir and the river. We wanted to look at the base cost of each zone in order to determine their individual variance, so we also excluded the $100,000 base cost that each zone would have, so the difference between each zone would be a lot more clear. This was a necessary customer need, as our specification required that the entire cost of the model be under $550,000. So finding the base cost would be important to determine how much money could be used for optimization. The additional future cost is another aspect that needs to be compared, as it could lead to future damages, causing our model to be less efficient and would cost additional money to repair. The complexity of land was considered, as the more bends the land has, the more efficient our model would become. The distance between the reservoir and the river was the final factor our team considered, as a longer distance between the two would mean a more inefficient model due to the energy loss of friction in the pipes, and a larger cost as more pipes would be needed in order to send water from the reservoir to the river and back. We changed each customer need to technical needs in order to compare them, and applied appropriate weights to each of them in terms of how important they were and how much they affect our model. In the end, Zone 1 was the most optimal choice, as it provided the lowest base cost, a less complex landscape than the other zones, and the shortest distance between the reservoir and the river. Zone 3 failed at having a low base cost, as the base cost alone exceeded the $555,000, and Zone 2 had the largest distance between the river and the reservoir, causing it to fail that technical need. With the information of what zone our model was going to be on, and the specific equations that allowed us to build our model, our team was ready to move on to cost and optimization as our next part.
Upon determining that Zone 1 would be the best area to build the hydro storage power system by using the decision matrices, there were still many other factors that needed to be considered, which is where the Python modeling system came into play. The team designed a program that would enable the user to input descriptions of the materials that they wished to use for the system, and based on calculations for energy and efficiency, if the efficiency is greater than 75%, which is the technical requirement, the program will output all of the possible combinations of the different wall heights and pipe diameters that will lead to sufficient efficiencies, along with the total cost of building that system and a ratio between the efficiency and cost. When the program is run, it prompts the users for inputs on the zone, for which they may choose from 1, 2, or 3, the pump efficiency, for which they may choose from cheap, value, standard, high grade, or premium, the pipe friction factor, for which they may choose from salvage, questionable, better, outstanding, or glorious, and finally, the turbine efficiency, for which they may choose from meh, good, fine, superb, or mondo. The program then determines other factors, including the pipe length, bend coefficients, and elevation, based on their choice of zone. Lists of unit prices for each factor, based on the other conditions and inputs, are stored and returned for use in the cost calculations, which come later in the Python program. For example, there are lists for all of the unit prices for each type of pump efficiency, each type of pipe friction factor, and each type of turbine efficiency. The program then iterates through all of the possible wall heights, which range from 5 meters to 20 meters in increments of a half meter, and through all of the possible pipe diameters, which range from 1.5 meters to 3 meters. Through this nested for loop, the program calculates all of the intermediate variables, such as the mass of the water in the system, the energy that is required to be input to the system, the area of the reservoir, and the draining and filling times. Based on these calculations, the program only prints the results of a combination that has an efficiency greater than 75% and a drain time less than 12 hours. It also then outputs the cost of each sufficient system and the ratio of efficiency to cost. When the team was testing this customizing function to find the most optimal design choice, besides already knowing that Zone 1 was the most cost-efficient choice, it was found that the pump efficiency had to be at least of standard value, the pipe friction factor had to be at least of nice value, and the turbine efficiency had to be at least of superb value in order to produce any system that was efficient enough to be above 75% efficiency. Based on this knowledge, the team continued to test the various combinations of Zone 1, standard high grade or premium pump efficiency, nice, outstanding, or glorious pipe friction factor, and superb or mondo turbine efficiency. The team then analyzed the efficiency to cost ratios to find the highest ratio, signifying a high efficiency and a lower cost, to find the most optimal choice for the hydro storage system design, which we will present on later. But first, let's switch over to Python to visualize how the program is run and how it is to be used by the user. As you see here in the beginning, it gives the user some directions on how to use the program. It then prompts the users for some inputs based on the zone, the pump efficiency, and pipe friction factor and turbine efficiency. Up here are the various factors that are affected by the zone choice. And also throughout here are the different lists that are created based on the user's input on turbine efficiency, pump efficiency, and pipe friction factor. For the calculations, it goes through the nested for loop, like I said earlier, of all of the possible wall heights and all of the pipe diameters, and it does the calculations for energy and efficiency. And after that, it then iterates through the series of if and elif statements that correlate to the different costs that will be needed for the end total cost equation. So this section talks about wall cost. This is the turbine and pump cost. And here is the pipe cost, and the bend cost. And then this section talks about the different costs that are specific to the zone choice. And then of course it calculates the total cost and the ratio, which is system efficiency over total cost. And of course, if the system is above 75% efficient and the drain time is less than 12 hours, then it actually prints all of the results of that specific system. And then the user can then analyze how they chose their design parameters. And this last section of the code talks about specifically the optimizing function, which simply prints out the results of the most optimal design choice that the team had found during the testing periods. So if the company was looking to find the most optimal design choice that we had determined in testing, they will type in optimizing. And here it will explain all of the parameters about the most optimal design choice that we had found in our testing period. If they wanted to customize on their own, they would type in customizing and then choose the zone that they intend to use, say 2. So they want to use a high grade pump efficiency, a glorious pipe friction factor, and a superb turbine efficiency. Then it will print out all of the different combinations that correlate to a sufficient efficiency above 75%. Team 10 found that the most optimal design choice is to use zone 1 to make a reservoir that has an area of about 95,892.517 square meters, to use a wall height of 13.5 meters, to use the premium pump, an outstanding pipe friction factor that has a diameter of 3 meters, and is 67.08 meters long, because we have decided to utilize the ground piping, which means that it will run along the hypotenuse of this triangular slope. Team also has decided to use a Mondo turbine efficiency. And overall, this design has an efficiency of 81.235%, while having a low cost of only $518,410.32. Which means its efficiency to cost ratio is the highest out of all of the combinations at about 1.567 times 10 to the minus 6. And that is our proposal for the most economical solution for the hydro storage power generation system.